What is up, Algebra 2 students? I'm going to do the review for you guys, so you can know how to do all the problems. We pretty much go from easiest to hardest. Maybe, maybe not. Unit 7 is definitely the easiest. Polynomials. We are add, subtracting, multiplying, dividing polynomials. Adding polynomials. Don't worry about the parentheses. You're not distributing because you're not multiplying. If you have like one basket of stuff and you have another basket of stuff and you pour it on the table, you're just going to combine all your stuff. All of your apples go with your apples. I have 3 apples, 1 from this bag, 2 from this bag. I got 3 oranges. That's all I got though. No more oranges for me. I have 1 pair, but I owe somebody 5 pairs. So I guess I owe 4 pairs. I owe an X to somebody. I have 12. I owe 13. I owe 1. All right. What I like to do is always change things to add the opposite. So if you want to, this could be a negative 1x. This is a negative 13. So this is a plus a negative, plus a negative, plus a negative. That's totally fine. I think that's what's helpful, especially for subtraction. Because subtracting, taking away all of these items from this box of items is the same as adding the opposite of all of the items. This is what I do, even my calculus students class. It's just like, add the opposite, don't make mistakes. Combine your like terms after throwing everything out on the table. 1x cubed, 5x cubed, I got 6x cubes. Negative 6x squared, that's all I got. Negative 1x plus negative 2x is negative 3x. You can always check this with a calculator, guys. I have 6, I owe 3, I have 3. Okay. Now, multiplying. When you multiply numbers, you just like find an area, like 3 times 2. What's 3 times 2? It's 6. Well, that's the same as finding the area of a square with a length of 3 and a height of 2. You kind of fill in the box, right? That's the area of that rectangle. So this is why we use the box to multiply. It's because I'm trying to figure out like the area if I have a length of this plus this plus this and a width of this plus this. Now, the key things to remember is how do you multiply 3x squared and 2x squared? How do you multiply 2x squared and 2x? Well, like 3 times 2 is 6, but x squared times x squared. That's 1, 2, 3, 4 x's being multiplied together. If you want to use a rule, fine. Just know where the rule comes from. 2x squared times 2x. 2x, 2 times 2 is 4. X squared times x is not just like 2 times 1. It's not 2. It's 1, 2, 3 x's being multiplied together. So this is 4x cubed. And we keep going on. And typically, there are some like terms that can be added when you're adding all of your boxes together. And we have some x squareds that are like. All right, functions increasing and decreasing, polynomials increasing, decreasing, positive and negative. First thing to remember is the degree. Even degree are like x squareds. X squareds are like up and up or down and down. Odd degree, like x or x cubed, they go this way. That would be x. X cubed would go this way with a little bit of curve. This is very much like x cubed, so it's an odd degree. And it's not like positive x. Positive x would look like this. Positive x cubed would look like that. So it's got to be the flip, a negative odd. So that's the leading coefficient. Now for the rest of them, for B, C, and D, we like to talk about intervals of x's. X's, where f is increasing or decreasing. So let's go with increasing up here, decreasing down here. Now we start at negative infinity, that's the first one that I'm going to circle. And you're going to look from left to right for these questions at B and C. Look from left to right, okay? The graph is going down, down, down. It will keep going down, 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 down until this -2. I'm going to circle the -2 and say my first interval is from negative infinity to -2, and that's when my function is decreasing. And then we're going to go up, 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 and up, and up, and up, and up until 3. So the second interval will be from -2 to 3, and that's when my function is increasing. Then the final interval will be +3 till, sorry, that's positive infinity. And my function's going down, 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 down. So +3 to positive infinity, we're going down. All of these combined make up our entire negative infinity to positive infinity interval. So we're good with that. Now we're going to start over and do the same thing, only for when f of x is less than 0. That means f of x is negative. Negative means below the x-axis with the y values. F of x is positive. That's when f of x is positive or above the x-axis. Okay, so C we're talking about negative, D we're talking about positive. We still do the same kind of process. We start at negative infinity, circle negative infinity. My first y's are positive until this value. So that's -2, 3, 4. Negative infinity to -4. This one is negative, this one is positive. So negative infinity to -4. It's the first one. Then we're going to be negative, 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 as in below the x-axis, below the x-axis, below the x-axis until 0. So the next interval is -4 to 0. And then above the x-axis, above the x-axis, above the x-axis until 5. So 0 to 5, we are above the x-axis. Below the x-axis, below the x-axis from 5 to positive infinity. So this covers every single interval from negative infinity to positive infinity. Part E, what are the end behaviors? This is different. This is your arms. I like to call it the arms. What do I mean by arms? It's like which way is your arms pointing? Which way are your arms pointing, okay? This is a negative x cubed. So I think this is how it's going to look like for you guys on the film. Okay? As I go to the left, I'm going up. As I go to the right, I'm going down. So your end behavior is as x goes to the left, my y's are going up. As x is going to the right, my y's are going down. As x goes to the left, my y's go up. It's your arm direction. As x goes to the right, my y's are going down. This is different from going left to right. This is going from the middle out. As x goes to the left, my arm's going up. As x goes to the right, my arm's going down. Cool. Unit 8 is factoring. To solve, it should be like solving polynomials should be like getting answers by factoring. Key things to remember, guys, with factoring. Like, you got to understand multiplication. If I did x plus 2 times x plus 3, well, you could do it here if you want to. I'm just going to show you the example. You realize you get x squared plus 2x plus 3x plus 6. What happens when you add things together? You get x squared plus 5x plus 6. We are going to take a polynomial. We are going to factor it. The reason why we factor it is because it's easy to find the solutions when this is equal to 0. Factors lead to solutions. Solutions are the values that make zeros in all of my factors, okay? So that's one thing. What's another thing? Well, you could multiply all of this by like 2, and this would be like 2x cubed, 10x cubed. So like the whole purpose of Unit 8 was factoring, and when we factor, we can then solve. We turn sums into products. Now, always look in step 1 for a greatest common factor. I can pull out x, and x times x squared is x cubed. Whenever my cursor comes back. There it is. X times x squared, x times negative 7x, x times negative 30. So x times x squared minus 7x minus 30. Now, again, I just showed you, this is a quadratic. X squareds plus x's plus numbers. This can be factored to be x plus a number times x plus another number. Your goal is to find the two numbers. How do you find the two numbers? Well, the two numbers add, like I did with x plus 2 and x plus 3. The two numbers add to get the middle term. 2x plus 3x is 5x. So I need two numbers that add to get the middle term. And those same two numbers need to multiply to get the last term. Okay? And the way we do this is sometimes we use this graphical organizer where you put one of the numbers here, one of the numbers here, just keep track of which one goes with which. I don't think this is necessary if you just can understand this looks like this, find the two numbers. The two numbers are negative 10 and 3. This works out. If you multiplied x plus negative 10 times x plus 3, you'd get x squared minus 7x minus 30. So I would put the numbers here if you wanted to, but then make sure you write it like that, but whatever. Now, this is the factored form. If I asked you for the solution, it's the x values that make zeros. Well, the x value that makes this 0 is 0. The x value that makes this 0 is positive 10. The x value that makes this 0 is negative 3. Bang, bang, boom. Okay, again, we know this can look like x plus a number times x plus a number. Why? Because if you multiply x plus a number and x plus a number, you get x squared, amounts of x, number. 2x plus 3x is 5x. So there you go. One number, two numbers have to add to get the middle, multiply to get the last. This is just an example. In my situation, I need the two numbers that add to get negative 4 and multiply to get negative 12. You can put the two numbers there if you'd like to help you solve the puzzle. Negative 6 and positive 2. Negative 6 and positive 2 multiply to get negative 12. They add to get negative 4. That's the factored form. We set that equal to 0. We get the solutions. X equals positive 6 is the x value that makes this factor 0, and x equals negative 2 is the x value that makes that 0. If I gave you something like x squared minus 16, you could do the same thing. It's like, okay, this has to equal x plus a number times x plus another number. But the two numbers have to multiply to get 16 and then add to get 0 x's. This is where the whole idea of the difference of squares and the special cases comes into play. X plus negative 4, x plus positive 4. If you multiplied x plus 4 and x minus 4 together, you get x squared, 4x, negative 4x, and negative 16. The x's would go away. That's how you get x squared minus 16. Okay, so what you notice is that if you square rooted this, okay, that becomes x. If you square rooted that, oh, that's 4. Make sure you have a negative and a positive. This is how we do this. If you square root 4x squared, you get 2x. If you square root 49, you get 7. You could factor this to be 2x plus 7, 2x minus 7. Now, there's no way to easily explain why the sum and difference of cubes are what they are, but it's the same process, only we're going to cube root or do things to a 1/3 power. I hate this one because nobody remembers it, and there's no reason for you to remember this. It doesn't show up on any exam, sum and difference of cubes. You have to remember SOAP and the rule, which I like to remember. It's the only thing I remember. It's the first, the second, the first times the first, first times the second, second times the second. We'll call m's the first, n's the second. This is just a rule to remember. I don't love it. First, second. First times the first is x squared. First times the second is 4x. Second times the second is 16. Then we remember SOAP. SOAP. S stands for same. Same sign as what's up here. So, minus. O stands for opposite. Opposite sign is what's up here. Plus. AP stands for always positive. We will always have positive things there. If you wanted to go ahead and distribute that out, you would see everything cancels out, and you're just left with x cubed minus 64. It's a fun thing that works out that way. Another one, if I took the cube root of this, 27 to the 1/3 is 3. 3 cubed is 27. That's this number here. 8x cubed is the cubed root of 8. 8 to the 1/3 is 2. So 2x. And again, it's first, second, first times first. First times first is 2x times 2x. That's 4x squared. First times second is 6x. Second times second is 9. Same sign, opposite sign, always positive. Great. Now, our goal is to set these equal to 0 and solve. Now, for this one, we're going to have to solve these equations. Minus 7 divided by 2. X equals negative 7/2 or negative 3.5. You get x equals positive 7/2 over here. So remember, we factor so we can solve. For these, we only get one solution there. The other two solutions we would get would be imaginary solutions. So positive 4, positive or negative 3/2, we'd get imaginary solutions from there. Unit 9, simplifying exponents. Here's the key. A square root is the same as a 1/2 power. A cubed root is the same as a 1/3 power. So to help you do some things, there are exponent rules, but if you don't remember them, you can always figure them out. 4x cubed squared. All right, well, that's 4x cubed times 4x cubed. That's 4 times x times x times x times 4 times x times x times x. What do I get? 16x to the 1, 2, 3, 4, 5, 6. This is a big mistake. A lot of people think, okay, 4 squared is 16. 3 squared is 9. My answer is 16x to the 9th. No, it's not. It's just 16x to the 6th. When in doubt, write it out. Now, if you got multiple things and you got a fractional power, well, everything can be taken to this 1/2 power. Now, it's tough to write out this, but it's kind of easy to understand. Like, I doubled my x cubes. 3 times 2 is 6. If I multiply or halve the 8x's, I'll have 4. If I have the 12s, I'll have 6. If I have the 16, I don't get 8, though. This is where it's tricky. Numbers can be written and plugged in. 16 to the 1/2, or the square root of 16 is 4. So it's like exponents have their own rules, numbers have their own rules as well. It makes sense that when you know that 3 squared is 9, 3 to the first is 3, 3 to the 0, you can plug in, you get 1. That when you take a negative power, you end up with the same thing as the positive power in the bottom. Like 3 to the negative second is 1 over 3 squared. Okay, you're just dividing everything by 3 every time you go down a power. So, negative powers are the same as a positive power in a denominator. The 2 is not taken to the negative power. If it was, it'd be like this, but it is not. So leave the 2 alone, it's not bothering anybody. Move the x down to the denominator, write it as a positive power. Got a cubed root, it's the same as a 1/3 power. You could take both of these terms to the 1/3 power. Power to a power, yes, it's like 1/3 of the x to the 12ths. You do multiply your powers. It's tough to kind of figure that out, but you can always go back to thinking about what happens to these powers if it's a power to a power. Well, if x squared 3 times, that's 2, 4, 6 x's. Okay, I multiply. Okay, 12 times 1/3. Okay, I multiply. 64 to the 1/3, though, is not going to be 64 times 1/3. That's not what I want. I want 64 to the 1/3. And that's 4. For these questions, I like to give out like stuff like the square root of 9 16 x to the 16th, right? This is the most important one because you see 16 twice. However, the square root of 16 is 4, but the square root of x to the 16th is x to the 8th. So we have 2 different 16s, but we get 2 different numbers. Like if you want to write down one single example, that's your example to help you remember how to do these. All right. Solving, whatever we're solving, anything from this entire course, it's always good to isolate what the x is in, whether it's an absolute value, a log, if there's an exponent involved. Isolate so we get like whatever x is in by itself completely. I'm going to subtract 3. Golf keeps turning off. To get rid of the 3. I'm going to divide by 6 to isolate the square root. Super duper important to get the thing that x is in isolated. Now just remember, to get rid of powers, you're going to use your exponent rule, where like a power to a power, you multiply your powers. Nobody's lighting the world on fire today. So if I have like x squared and I wanted to get rid of the square, well, I'd use a 1/2 power because 2 times 1/2 is 1. If I have x to the 1/2, I'd square because 1/2 times 2 is 1. If I have x to the 2/3, I would take both sides to the 3/2 power because 2/3 times 3/2 is 1. So just remember that reciprocal powers are used. Square things when they're square rooted because that's like squaring a 1/2 power. Square both sides, I get x plus 2 equals 4 squared. Subtract 2, subtract 2. X equals 14. All right, exponential functions. My favorite unit. Remember our project? No? Whatever. We have a starting value. We have 1 plus or minus an r. You can consider r positive if we're growing. You could consider r negative if we're decaying. Or you could consider a 1 plus r, r always being positive for growth, and 1 minus r, where r is positive for decay. This is going to be to the years. A is your initial amount. R is your rate. X is your years. But we could change this. If we're compounding continuously, we're going to have our initial amount e to the r, x, r rate. It's It's not exactly like in terms of a percent, at least I don't think. And if we're compounding multiple times, so I'm going to give you like a 1/12 of your percentage 12 times, you're going to take your initial, you're going to split up your percent you're given every year an amount of times, and you're going to give it to them that many times per year. Hopefully that makes sense. Like, ooh, it's windy out there. It's going to be tough. Hopefully that makes sense. Like if I wanted, if my bank was going to give me compound me quarterly, most banks do it monthly. Quarterly, they would say, I'll give you a quarter of your percentage, but I'll give that to you 4 times a year. Okay? Anyways, we have our equations. We start with 1,000. We have our rate. Please change your percentages into decimals. R is 0.087. You move the decimal place over twice, or you take Mr. Calculator, take your percentage and divide it by 100. That's 0.87%. So I got 1. I'm growing an amount of investment, so I'm plus 0.087 over 12 to the 12 amount of years, giving you a 1/12 of your 8.7% 12 times per year. If this number becomes infinity, the magical value E pops up. Is it a walk and talk with DJ?
Everything becomes easier from there.
No. All right, E to the 0.087x. Cool. Now, in Desmos, we would plug in values for x to get amounts. We would plug in values for y to solve for certain amounts. I'll show you how to do it on your calculator. You can also do it on Desmos. All right, we got a depreciating truck. We're depreciating. You can consider R negative. We did this study. Current value, initial value. So I have a $53,000 truck that is losing 16% per year. You could probably do this math a little bit, especially when we get into solving exponential situations using logs, though we don't really do that on this review. We get 0.84 to the x. That could be your equation. What is the value 3 years from now? When x is 3, what is y? So you just plug in 3 for x. $29,635. All right, I don't like to call it rewriting. I like to call it solving. I'd like to put an X there, but whatever. Key thing that we learned is probably the most important thing, that exponents and logs are the inverses of each other. They're like square rooting and squaring. In a previous question, I had to solve a square root. How do I solve a square root? I square. If I have an exponent, how are you going to solve? You're going to use a log. If you have a log, how are you going to solve? You're going to use an exponent. So, if I have an exponent, how I'm going to move things around? I'm going to use a log. I'm going to take the log 625 of both sides. The log 625 of 625 to the exponent goes away. I get 0.25 equals the log base 625 of 5. We know how to plug this into our calculator, most of us. It's either using log base, and there you go, that's what you're supposed to get, or you do the log of the big number divided by the log of the base. It's not the big number, the log of the top number divided by the log of the base. Okay, so I have 19 to the power of 0. I can log base 19 both sides. To get 0 equals the log base 19 of 1. And that checks out if I plug in the log of 1. I get 0 divided by the log of 19. I still get 0. All right. If I have a log and I want to get rid of it, I will use a number to the power, an exponent. To get rid of logs, use exponents. So it's this number I pay attention to. You see that base of that log, get rid of that log base 2 with a 2 to the power. 2 to the log base 2 goes away, gives us just 32 equals 2 to the 5th. If you don't see a number, there's a 10 there. If you see ln, there's an e there. Okay, so e to the power would be getting rid of that. 10 to the power would get rid of that. This gives me 1000 equals 10 cubed. I wish we like solved things so you can like see how to get the number where 3 to the x equals 1000. You know, what's that number? It could be a decimal, it's fine. And what we find is logs and exponents are inverses of each other. To determine if things are inverses of each other, you could compose them. Like, what happens if I plug one inside another? If I only just get x, what I started out with, I win. Now I'm going to show you two different ways, the easy way that I kind of showed my students and then the hard way, which was done in most classes. What we did in my class is we said, hey, find f of g of a value like 2. If you get 2, they are inverses, okay? And my students worked on plugging in 2 into g. So g of 2 is 3 minus 2, which is 1. Okay, cool. This becomes f of 1 because we just found g of 2 is 1. Now, what's f of 1? Well, I plug in 1 into f, and I get 5 times 1 plus 4, and that's 9. So, what do I notice? F of g of 2 does not give me 2. So, no, they are not inverses. This is the easy way to do it. Just use numbers. The hard way to do it is to use the equations. F of g of x would be f using 3 minus x. Now, instead of x, I'm going to replace it with 3 minus x. So instead of x, I'm going to replace it with 3 minus x. So that becomes 5 times 3 minus x plus 4. I multiply everything together, I get 15 minus 5x plus 4. Obviously, you don't get just x, so the answer is still no. Let's change this to a g of x. Our bad. And let's do something. F of g of 2. Okay, let's see what we get. Hopefully we get what we started with. Okay, 2. G of 2. Cube 2 is 8 minus 5. 8 minus 5 is 3. Okay, so this becomes f of 3. Does f of 3 give me 2? Let's see. Plugging in 3, I get 3 plus 5, which is 8. The cubed root of 8 is 2. So f of g of 2 is like 2. So it's like I did something to 2 with g, but then f brought it right back to where he started. Poof! They are inverses of each other. They undid each other. So that is using numbers to confirm that. But if you want to check if these actual equations are inverses all the time, that was just like an example, you would have to compose them. F of g of x becomes f of x cubed minus 5. Wherever I have x, I'm going to plug in x cubed minus 5. This becomes the cubed root of x cubed minus 5 plus 5. X cubed minus 5 went there. The 5's go away. The cubed root of x cubed is just x. So the g, what it did to x, f undid it. It just gave me x. It's like nothing happened. To undo things, all you need to do is to solve for the variable and just like have, I like to use a's and b's in my class. Sometimes it's like flip-flop the x's and y's and then solve for y, but really it's like get x by itself. Well, how would you get x by itself to undo what's going on in y? Well, I would subtract 3 to get y minus 3 equals negative 1/2 x. Then I would multiply everything by negative 2 to give me negative 2y plus 6 equals x. This is the inverse function. Now, it's probably best if you have it like flip-flopped, but this is just a linear function. We don't really use inverses in linear functions. All right, part of Unit 11 was what we did here, the whole rewriting of stuff. Logs undo exponents. Logs work like exponents. Logs, exponents, arch enemies of each other, or best friends, who knows? But since they work like exponents, they have very similar rules. For example, a power to a power, if you have this, this is a little tricky. For example, if you have multiplication, you can actually split things up like addition. If you have a power to a power, you can bring down and multiply that power. I'm not even going to go into this because log properties, used in very advanced math classes to sometimes simplify answers. They used to be used a lot more often when we could not plug in logs into calculators and we had to look up values. So sometimes like expanding or compressing could help make those calculations simpler. These days it's not very important, honestly, log properties. Division is the same as subtraction. Bring down those exponents. What I like to do is this with numbers. How you can see log 5 minus log 25 is the same as the log of 5 divided by 25. Look at that. So, subtraction is the same as division because it's like an exponent rule. Log 5 over 25 or log of 1 over 5. Take the log of 1 over 5, and it's the same as the log of 5 minus the log of 25. This is the log of x to the fourth. All right. Solving exponential equations, hooray! This is the fun stuff. What I told my students, isolate the exponent. Okay, so look at part B. E is not by itself. I need to get rid of the 7. Ooh, 8. Okay. The 10 is by itself. In the exponent, we got 2x. Okay, cool. So now we are ready to get rid of this 10. Wish there was more space. So I can show you that to get rid of the 10, you log base 10. A log is the inverse of an exponent. A log base 10 will get rid of a 10 to a power. Log base 10 of 10 to the 2x, that goes away, gives me 2x. You could type log base 10 of 57 into your calculator. You get that. Well, solve for x divided by 2. There you go. You could also say this is the same as the log base 10 of 57 divided by 2. You want to get rid of the e, you log base e. How do you log base e? Well, you could use a shortcut and do the natural log. The natural log is the same as log base e. So the natural log gets rid of e to the power. Since it's used so often, this e to a power, it gets its own button. You can type in the natural log of 8, 2.079, divide by -2, divide by -2, and you will have solved for x. -1.039. Okay? You want to get rid of, why do we do this? All right, we go from like fine to hard. So here we go. You want to get rid of a log? You use an exponent. You don't see the base, but it's there. Log without any number is a base 10, so I'll use 10 to the power. I get 3x plus 1 equals 10 squared. Now this is 10 squared, not 10 times 2. It's an exponent that is undoing the log. Okay, the 10 to the log base 10 goes away. 10 squared is 100. Subtract 1, divide by 3. Voila. You could take 2 to the power of everything, but I wouldn't recommend it. What you should do is use exponent rules to combine them. Actually, no, you know what you could have done? What's log base 2 of 5? This is just a number. What's log base 2 of 5? It's just a number. Okay, so I'm going to rewrite this question. Log base 2 of 10y minus 2.321 equals 3. All right, add that number to both sides. Get rid of it. Let's not go crazy. There are other ways to do this, but let's just take it easy. So I'm going to add that to 3. I get 5.321. Okay, so log base 2 of 10y equals 5.321. Okay. I want to get rid now of the log base 2 because the y is inside of it. I will use 2 to the power of both sides. I will go 2 to the power of that number. Look at that, 40. Isn't that incredible? 10y equals 40. Then divide by 10. There are other ways to do this question, but whatever. The old Richter scale problem. M is the Richters. E is the energy. 6 equals 2/3 log E over 10 to the 12th. Fantastic. Get rid of the 2/3. Divide or multiply by 3/2. All right, start with that. Use parentheses if you're dividing by a fraction. 9. Get rid of the log base 10 using a 10 to a power. This is 10 to the 9th equals E over 10 to the 12th. Now I wonder, like, 10 to the 9th times 10 to the 12th. Oops. Yeah, I mean, it gives you like 10 to the 21st. A lot of energy. I'd solve this by multiplying. Okay, bringing us to the last 2 units, the rational expressions, where we're adding, subtracting, multiplying, and dividing, and solving fractions. Starting with simple ones where there's no addition, so all you have to do is use like division rules and exponent rules. 25 divided by 5, you can divide the top and bottom by 5. So take care of that. That becomes 5 over 1. I have 2 A's that'll cancel with 2 A's here, leaving 3 A's in the bottom. This is the same as subtracting, but wherever we start with more of, that's where we're going to end up. This is because every time you have an A over an A, they are replaced with a 1 over a 1, okay? So there is like a 1 up here, 1 down here, whatever. You get that, okay? Do the same thing here. I'm going to divide the top and bottom by 5. Both of my x's will cancel and leave 1s. 5 of my y's will cancel with 5 of these y's, leaving me 3 y's. I'm subtracting there. I get 9 over 6. Oh, I could have divided by 15. Silly, Mr. Messner. Almost those.
What comes to your mind? Don't make me cry. Seriously, it was my last little goal that I have for my career, and to make it happen is really cool. And for all the support I have is fantastic. For the 29,000 PGA pros out there, thank you. You mentioned the fact that you do want to be the low professional here this week and be on that 18th green when the trophy's handed over to whoever wins this championship, and you're only 4 shots out of the lead. It could very well be you in that regard. I wonder at this position after 36 holes, what impact does it have on maybe changing your goals for the weekend? My game's good. I got it. I'm peaking right now. The greens are beautiful. The course is great. I'm driving it well. So I have an opportunity to move up the leaderboard, to be honest, and I look forward to playing Saturday and Sunday. You look like you're having fun, and from a
Don't get cocky.
standpoint, we'd like to see the best athletes in the world, whether they're competing at this level, enjoy it as well. How much fun are you actually having? First of all, I'm not one of the best athletes in the world, but I am having a great time. I have no pressure. I've got a job. I've got a paycheck waiting for me at my club. So I don't have to make putts this week. I don't have to make the cut to earn a paycheck and pay for my mortgage. So this is just a beautiful thing I have here. Rochester's been amazing. The people in Rochester are fantastic, and my team's fantastic, so I'm a very lucky guy. Well, after 2 rounds of even par 70, you've been playing fantastic, Mike. We appreciate it and look forward to seeing you tomorrow.
So this is a cool story. This guy, Michael Block, he's a golfer, and he's just like a random club professional. So think of it as like a high school coach or something like that. Well, this like random high school coach is playing in one of the hardest tournaments in golf, and he made the cut. So he's like playing better than a lot of like professional tour players. So think about like a high school coach being allowed to play in an NBA game, but then like getting 20 points in a game, just like randomly, like it happens in sports sometimes. Stuff like this happens, and it's really cool when stuff like that happens. It shows like people can get hot. Cool things can happen. Anyways, those are easy. These are when it gets tough. You see this addition? Because of this addition and the subtraction, first things first, you're not allowed to cancel. You're not allowed to do that. You're not allowed to divide by x or like cancel or divide by 3 over 3. No. Your goal is to factor. You have to factor to create multiplication. Now, how do we factor? Well, we might need to factor a greatest common factor. We might need to see a special case. Now, the reason why I do this is because when you're multiplying fractions, if you remember with numbers, you just multiply the top and bottom together, like 2/3 times 4/5 is just 8/15. You multiply the top and the bottom together. So it's almost like you can write it as one fraction, 2 times 4 over 3 times 5. And what's great about this is like, let's say I change some numbers. If this was, 3/4, well, I could maybe just say like, well, that 3 over 3 is just a 1 over 1. It's gone. And this 2 over the 4 is just like a 1 over a 2. So like 6, 2/3 times 3/4 is actually the same as 1/2 or 1/4. I digress. All I'm saying is like if we factor, we can combine these two fractions because we're multiplying and just multiply all the terms together, or more importantly, cancel the terms that are shared and can be canceled. Creates ones over ones. Okay, so you get that. Remember when you're dividing, 8 divided by 2 is the same as 4, right? Well, that's also the same as 8 times a half, right? Isn't 8 times a half 4? Yes. Keep, change, flip. Keep, change, flip. We can change this to multiplication, provided we flip this to be x minus 2 over 3x plus 3. Okay? But we need to factor, okay? And we notice that these x squared plus 4x plus 3's, oh yeah, that's going to be an x plus a number times an x plus a number in the top. The bottom's the same thing. It's going to be x plus a number times x plus a number. This 3x plus 3, I could factor out a 3. So I have 3x plus 1. And the top is x minus 2, okay? Now I just got to figure out all of these numbers here. So let's start with this one. Two numbers that multiply to get 3 and add to get 4 are 3 and 1. Two numbers that multiply to get -8 and add to get 2 are positive 4 and -2. And since we are now multiplying by the flip, we can combine all of these terms, multiply them together, and more importantly, cancel and simplify our fraction. Typically, we never want to multiply out in the denominator. We just want to leave it like that. Okay? Now, that is multiplying and dividing fractions. Adding fractions. What if I asked you to add a half and a third? What do you need? A common denominator. How do you give it a common denominator? Well, sometimes the easiest way is to give one the other's denominator. So multiply this by 3 over 3 and this by 2 over 2. And I get 3, 6, and 2, 6. I get 5, 6. Well, that's the same idea here. To give this a common denominator, you can't just like add 3 and subtract 3. You have to multiply by x minus 3 over x minus 3. You have to multiply by x plus 3, x plus 3. Now what happens is I know my common denominator is going to be x minus 3, x plus 3. I'm just going to leave that. The key is to just figure out what's in the numerator. Well, you just got to add your stuff. Got to love the printer. Well, you got to know what stuff you have. Well, from this guy, I have 4x squared minus 12x. I distributed the 4x to the x and the -3. From this guy, I have 5x squared plus 15x. Now, what do I have? 9x squareds. And you could have done this like kind of separately and then just added stuff together. 9x squareds, 3x's, x minus 3, x plus 3. I don't think they'll ask you to factor from there. And that's fine. Okay, solving rational expressions. You would think, oh, we need a common denominator, but not really. You just need to first notice there's an equation, and you just cross multiply. This is like you guys thinking about butterflies. What you are doing is multiplying both sides by both denominators and canceling out like the x minus 7s and 5x's, but people don't want to see that. So anyways, it's 3x minus 21 equals 10x. Get all your x's onto one side. Divide to solve. All right. And then we finish off with this most recent unit, which we didn't test on, and that's okay. Where we started with our friend, y equals the absolute value of x. Absolute values are great because it keeps positive values positives, but it takes negative values and makes them positive. The transformations are the same as with quadratics, with anything else. Inside, x is opposite. This means I'm shifting left 3. Outside, y is normal. This is me shifting down 2. If I'm multiplying by 2, you're adjusting the slope. You make it skinnier. This is a vertical stretch. Your slope is now 2. Why do I say slope? Because we are really dealing with two linear equations, y equals x and y equals negative x. So the slope would be up 2 over 1, up 2 over 1 in both directions. So this is also right 1. Here, since I'm going left 1, I'll have an x plus 1, and I'm going up 3, I'll have a plus 3. I see the slope is up 1 over 1, so this stays as 1. Here, I see I go to the right 1, I go up 1, but my slope is negative 1, so I'm going to put a negative 1 in front of that. Flip it vertically. I remember this question. It's a good question. Here, I go to the right 6, so I need an x minus 6. I go up 3, but my slope is down 1 over 2, down 1 over 2, down 1 over 2. So this is why I need this to be a negative 1/2. I remember this question. I think they were wrong, but let's see. Shifting to the left 2. Okay. Skinnier. Slope of 2. Okay. Flipping. Well, I know this is the only one that's flipped. Up 1. That's got to be it. It ends up being like a horizontal compression, which is a vertical stretch, but it's fine. All right, solving algebraically. Once you have your isolated absolute value, we understand that the inside of the absolute value could equal negative 10 or positive 10. We then solve both equations to get both solutions. Okay, negative 2, positive 8, poof. Now with inequalities, we have an absolute value and a number. What is the absolute value below my number or less than the number? That is going to be the interval between two numbers. What I like to do is say to my students, find the two numbers where they're equal, and then write your inequality for x's that are between those two numbers. So I'm going to add 8 in both instances. I get 6 and 10. My x's have to be between 6 and 10. This is between 6 and 10. You can write it like this or like this. I like this. This is good practice for you guys. I told students to do this like with Desmos. I wouldn't do it graphically, honestly. Let's just do it. You know that the solutions, again, are going to be between, but since it's less than or equal to, it's less than or equal to. You just got to find the two values. They're going to be negative 1 to get you 2 and negative 5 to get you negative 2. Again, you split this up because it's isolated. So x is between negative 5 and negative 1. Just as a heads up, guys, if this was in the other direction, all right, if this is in the other direction, we have the two tails. Now this is an or situation. This is when I have one or the other. I'm going to switch it up just for this problem because we've not done a problem like this. If it was when is the absolute value greater than 2, well, it is the x's that are less than my small number, or the x's that are bigger than my bigger number. Okay, these are the x's from negative infinity to negative 5, and here are the x's from negative 1 to infinity. Same here, like you don't have to solve by graphing, but if you want to, great. This is easy enough to do without graphing. When does x plus 3 equal negative 2 and x plus 3 equals positive 2? I mean, we just did it right here. It's negative 5 and negative 1. Voila, we did it! We did it! Yo, Algebra 2, it's been real. I've had a great time. I think a lot of you guys have grown in your competence and abilities, and hopefully you're not looking at math too negatively after this year. I'm always here to help. C100 Wing, reach out. You guys rock, especially my students. You guys rock. All the other students rock too, but especially my students. So if you're watching this, take care. Like, share, subscribe. Mr. Messner, 2K23, 2223, out!